Hello guys, welcome to the DMS online school. If you are new to this channel, you are most welcome, and on this channel I teach mathematics, biology, science, and also revise past examination papers. So if what I do on this channel is what you're interested in, please consider subscribing and turning on the bell notification. Without wasting much of your time, let's go into the day's lesson. Alright, so the day's lesson is on the concept of the limiting reagent and excess reagent. So let's look at first what the limiting reagent is. So the limiting reagent, by definition, we say it is the reactant that is used up or finished first in a chemical reaction. So in a chemical reaction, a reactant that finishes first is known as the limiting reagent. And then let's look at what the excess reagent is. So the excess reagent, we are saying it is the reactant that remains after a chemical reaction is over. So let us look at an example given below. In a scenario where we have nitrogen gas reacting with hydrogen gas to form ammonia gas, what we are learning is that this stoichiometric equation tells us that in the formation of ammonia gas, 1 mole of nitrogen gas requires 3 moles of hydrogen gas to form 2 moles of ammonia gas. So this equation, which is balanced like this, we call it a stoichiometric equation because it is balanced. So we have 2 atoms of nitrogen here. Also on the right side, we have 2 atoms of nitrogen. Then on the left side, we have 6 atoms of hydrogen. And also here, we have 6 atoms of hydrogen. So such an equation is a balanced equation, and we also call it a stoichiometric equation. So in this equation, we are being told that 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to form 2 moles of ammonia gas. So in this equation, all the reactants are converted into products. So such a balanced equation like this, all the reactants are converted into products. This means that whenever we are preparing ammonia gas, for instance, we must take into consideration these ratios. So if we are preparing in the laboratory or in an industry ammonia gas, we should be aware that in a chemical equation, this is how ammonia gas is formed from 1 mole of nitrogen reacting with 3 moles of hydrogen to form 2 moles of ammonia. So this is a ratio, or this ratio is the one which this equation follows. So whenever we are preparing ammonia gas, this must be followed either in a chemistry laboratory or in any industry that is trying to manufacture ammonia. So it's very, very important that we understand how important balanced equations are, because they tell us exactly the amount that should react completely to form a product, so that we do not have an excess reagent or a limiting reagent. So what we are saying here is that in such an equation like this one, it can be converted in this format, which enables us well to understand the concept of limiting and excess reagent. So I always put this equation in this format, which helps me to understand the concept. All right, so what we are saying here is that if we have N here representing number of moles, then we write nitrogen gas. So this is read as number of moles of nitrogen gas over 1, which is the stoichiometric mole ratio in the equation. We have 1 in front of nitrogen that we don't indicate. So this can be read as the number of moles of nitrogen over the 1 stoichiometric mole ratio is equal to number of moles of hydrogen gas, this hydrogen gas, over the stoichiometric mole ratio, which is 3. This from here, it has been put there, equals then also number of moles of ammonia gas over the stoichiometric mole ratio, which is 2. These two here. So this is how this equation can be converted into, and this format is very, very important in understanding chemical equation. So it is telling us that the amount of this whole substance must equal to the amount of this substance, and these two now must be equal to this amount. So for instance, let's say in such an equation like this one, this is how they react. Now, let's say instead of using 1 mole of nitrogen, then we use 2 moles of nitrogen here. If we use 2 moles, then we have not followed the stoichiometric mole ratio 1, 3, 2. So the moment we use 2, that means this equation must be offset. So for it to be balanced, 2 moles of ammonia gas must require now, instead of 3, they will require 6 moles of hydrogen gas. So 2 moles of nitrogen gas will require now 6 moles of hydrogen gas. And now it will not produce 2. It will now produce 4 moles of ammonia gas. So that's how this happens. It will form now 4 moles of ammonia gas. So making sure that everything balances as well. Also, if we decide to get 3 moles, instead of 2 moles, we use 3 moles here. If we use 3 moles here of nitrogen gas to form ammonia, for all the reactant to finish, then we must also use 9 moles of hydrogen gas, and that will produce 6 moles of ammonia gas. So what is happening? The moment we increase this one, this must increase in the same ratio, and this one must increase in the same ratio. If I use 2 here, then this one must be multiplied by 2 to get 6. This one must be multiplied by 2 to get 4. If I use 3 here, this one must be multiplied by 3 to get 9. This one must be multiplied by 3 also to get 6. That's how these ratios are changing. And in such an equation, when you are reacting 3 moles of nitrogen with 9 moles of hydrogen, all the reactant will finish, because no reactant will be in excess and no reactant will be limiting. No reactant will finish before the other, or no reactant will remain after the reaction. All the amounts will be finished at the same time. Nothing will remain, and then the product will be formed like that. Now, let's take for instance, instead of using 9 moles, let's decide we use 3 moles. We get 3 moles of nitrogen gas, then we react them with 3 moles of hydrogen gas. So in such an instant here, let's say we don't know what will be formed. We don't know what will be formed. So it's so easy. You see, following the actual equation, when we use 3 moles, when we are doing the actual experiment of preparation, instead of how the equation goes, because the equation must follow 1, 3, 2. Now, as here we are following 3, then here we are using also 3. Instead of 3, 1, now we are using here 3 as well. So, in such a reaction, you would find that this one requires 3 moles, requires only 1 more. 3 moles requires only 1 more here. But here you have provided 3 as well. So meaning these 3 which you have provided is more. So this one will only pick 1 and use it, and then that other 2 moles will remain because it will be in excess. It will only require 3 moles to react, because that's how the reaction goes. 3 moles of hydrogen will require 1 more. But if you have provided 3 moles of nitrogen, then they are in excess. Only 1 of that 3 will be used, and then you remain with the 2 in excess. And here will only form 2. Because no matter how much this one will increase, it will not alter as long as this one is limiting. So this one will be called the limiting, because 3 is less. 3 requires 1 more. Now you have provided 3. So 3 will only get 1 and then react to form 2 moles of ammonia. Then it will finish. Then this will remain with the 2, and then it will be the excess reagent. This one will be the limiting reagent. So we are saying in this case, nitrogen is in excess. Sorry, here I was supposed to write excess. So in this case, nitrogen is in excess. Hence, it's an excess reagent with excess 2 moles. And hydrogen is a limiting reagent, meaning it finishes in this reaction. All right. So let's move a bit this part here. So we are saying the limiting reagent determines the amount of product formed. In a chemical reaction, the limiting reagent is the one that determines how much of the product will be formed, because just as I said, if a 3 requires what? 2, but you have provided 3 in that reaction. So the limiting reagent or this hydrogen will only pick 1. When it picks 1, then it finishes, and then it forms 2 moles of nitrogen. Then that reaction will no longer continue, because 3 moles would have finished, then would have remained with 2 moles. Those 2 moles will have nothing to react with to form more ammonia. So once this one has finished, then the formation of ammonia stops. So this is what we are saying, or why we are saying the limiting reagent determines the amount of product formed. All right. So for online tuitions, guys, contact me on my WhatsApp line appearing on the screen. All right. So let's continue with the lesson. So let's have an example here. We have this example where we are saying urea with the chemical formula here is prepared by reacting ammonia gas with carbon dioxide as shown. So this is the equation for preparing urea with such a chemical formula. So this equation is balanced, because whenever you are calculating or you are answering problems to do with limiting reagent, you must make sure that the balanced or the equation is balanced. So they are saying in one process, 637.2 grams of ammonia are treated with 1,142 grams of carbon dioxide. Then they are saying A, which of the 2 reactants is the limiting reagent? Then B, calculate the mass of the urea formed. So this is urea. So they want the mass of the urea formed here when these 2 reactant ammonia reacted with carbon dioxide to form urea and water. Then here they're saying which of the 2 reactants is the limiting reagent. So of these 2, which one is the limiting reagent. Then B, they're saying calculate the mass of ammonia or urea, this one here, formed. Then C, how much excess reagent in grams is left at the end of the reaction. So when ammonia and carbon dioxide react to form urea, which one will be the excess reagent and how much in excess will be left out? All right, so let's look at the answer here. We don't have enough space. Let's squeeze a bit. All right, so we'll go back to the stoichiometric equation ratio. So we'll say number of moles of ammonia gas divided by stoichiometric mole ratio 2 is equal to number of moles of carbon dioxide over 1, which is the stoichiometric mole ratio here, then equals this product here, which will be number of moles of urea divided by stoichiometric mole ratio in front of urea, which is 1, equals number of moles of water divided by stoichiometric mole ratio in front of the water. Now you notice that in this question, they are not interested in water. So this part will fall and then remain with this as our equation. All right. Now, since they are saying which of the two reactants is the limiting reagent, so what we are going to do is to compare these two. So this one will fall as well, and then we'll remain with these two here. All right. So we want to find out which of these two is the limiting reagent. So by default, you must understand that an equal sign in front or in between here tries to show that what is on the left side must be equal to what is on the right side. So these are the mole ratios here according to the way the equation reacts. And number of moles here are the amount provided here. So number of moles of ammonia, the one that has been provided, which can be calculated from the masses provided here, and also number of moles of carbon dioxide can be provided or calculated from the mass provided. So what we are going to do is first to know the number of moles of ammonia and the number of moles of carbon. So let's calculate the number of moles of ammonia first. We know that the number of moles of ammonia can be found by this formula, which says number of moles is equal to mass over molar mass. All right. Then we'll say which is equal to, we'll get number of moles here, I mean mass of ammonia, which is given here, which is 637.2 divided by, then we'll get the molar mass of ammonia, which is 17. If you don't know how to find the molar mass and this equation, click on the video which is appearing above here. All right, because I already did a video on mole concept very well, and then you understand how I found this. All right. So now we'll say number of moles is equal to, when you divide 337.2 divided by 17, you'll get 37.48 moles. So this is the number of moles of ammonia in 637.2 grams, which we are supposed to have here. Then let's also calculate the number of moles of carbon dioxide. So number of moles of carbon dioxide, also using the same formula, is going to be equal to mass of carbon provided is 1,142 divided by molar mass of carbon dioxide is 44. Then we'll say number of moles is equal to 1,142 divided by 44. It will give us 25.95 moles. So this is the number of moles of carbon dioxide provided. Now what we are going to do, it is to replace now We know now the number of moles of ammonia. This one, it's this one here. So we'll put it back here on the top of the equation. So we'll say 37.48 divided by 2 is equal to, again here, number of moles of carbon dioxide, we know it is 25.95 moles. So we'll put it there, divided by 1. Then we'll divide 2 into 37.48, it will give us 18.74 equals, then 25.95 divided by 1 will get the same, 25.95. Then we'll compare, is this equal to this? No. So we have seen that this is not equal actually. This is not equal. All right? So this one, what we are seeing from here now is that on this one we have this one now can come like this. Instead of equal, it should now become like this. All right? So what we are seeing now is that according to the stoichiometric equation here, the number of moles must be all right. So what I'm saying is that so in this equation, it is not true that 18.74 is equal to 25.95. So 25.95 is more than 18.74. So it means this reactant here is in excess, while this other reactant is in less amount. All right. So what I'm saying here is that, let's squeeze a bit here. So what we are saying here is that ammonia, which is from this side, is less. Hence, it is the limiting reagent. So it is the limiting reagent because after putting these values in the equation, the way they will react, so we'll discover that this one will be less, this one will be more. So since they said which of the two reactants is the limiting reagent, the one with less amount is the limiting reagent. So ammonia is less, hence it is the limiting reagent. All right. I hope you are getting value in this video. If you are getting value in this video, please smash the like button and also let me know in the comment section. All right. So let's move and answer the second question here. So the second question says calculate the mass of urea formed. So we need to calculate the mass of urea formed. Again, we'll get the same stoichiometric equation, which is saying number of moles of ammonia over stoichiometric mole ratio in the balanced equation is equal to number of moles of carbon dioxide over stoichiometric mole ratio of carbon dioxide in the equation is equal to number of moles of urea over the stoichiometric mole ratio of urea in the equation. So now remember, what determines the amount of product formed is the amount of limiting reagent, because whenever one reactant finishes, then the formation of the product also stops. So that reactant that has finished has determined the amount, because the moment the amount finishes, then the product also stops being formed. So what has determined the product formed is now the amount of the limiting reagent. So it's only ammonia here that is going to determine the amount of urea that will be formed. So in this case now, our equation will come like this. So we'll only get the mole-to-mole relationship between the limiting reactant and also the product that will be formed, which is urea. So now remember, these are the number of moles. So for us to be able to calculate the mass of urea, first of all, we must know the number of moles of urea, then calculate now the mass from that. So we know for us to be able to calculate the number of moles of urea, we will use the same equation here. But we have already calculated the number of moles of what? Of ammonia here, which we said it was equal to 37.48 in the previous equation. That's how we calculated the number of moles. So this number of moles now, we already know it. We'll substitute it here. So we'll say 37.48. We have substituted. So this is equal to this. So we have substituted it here. Then divided by these two equals. Then this is what we want to find out. So it will remain the same. Then we'll say over 1. So we'll divide this side. 37.48 divided by 2 will give us 1874. Then equals. So remember, this one would have made this the subject of the formula. But we can't do that because we just have 1. So this makes our work easy. Any number divided by 1 is itself. So this value here divided by 1, it will be the same number of moles of urea. So this practically or technically tells us that the number of moles of urea is equal to 18.4 moles. So we have found the number of moles of urea. Now we need to find the mass of urea using this equation. Number of moles is equal to mass over molar mass. So we are going to make mass the subject of the formula. So if you don't know how to make the subject of the formula a quantity, then you can click on the video whose link is appearing here, because there I taught very well how to change the subject of the formula. All right, so I'll make mass the subject of the formula as shown. So it will be mass is equal to number of moles times molar mass. All right, so now what we are going to do here is to say equals. So we'll get number of moles of ammonia, I mean urea. We have already found it, 18.74 times. Then we'll find the molar mass. So the molar mass of urea, which is 60, then we'll say mass is equal to 18.74 times 60, which will give us 1124.4 grams. All right, so this will be the mass of urea that will be formed. All right, so if you are getting value in this video, please don't forget to give it a like and also let me know in the comment section. Right, so let's move a bit. Let's look at now C, which says how much excess reagent in grams is left at the end of the reaction. So we have determined already here. All right, so we already determined here that in such an equation, this will be the number of moles of ammonia that will react, and this will be the number of moles that will be provided for carbon dioxide. So these will be more. So since there will be more, then there will be some moles that will remain. So in short, this will pick its equal number from this and react to form urea, and something that will remain in here now is now going to be the excess. So what we are going to do here is this. So we'll say 25 minus, now in 25 you remove 18.74 because carbon dioxide, which is providing these numbers of moles, is the equal number of moles from this side that must react from here. Not so that what is on this side must be equal to on this side. So this limiting reagent is 18.74. Requires also 18.74. Now we are given 25.95. So it is in excess. So this will only pick itself 18.74 in this one. And that which will remain will be the excess. That's why we are saying, then we'll know the excess by saying 25 0.95 minus 18.74, which will give us 7.21 moles. So we have known now the number of moles in excess that are going to remain. Now we can calculate the mass using this excess, because here they are interested in the mass. So we'll say, okay, the mass is found by this formula. Mass is equal to number of moles times molar mass. Then we'll say equals number of moles now that will remain is this 7.25 times now the mass of carbon dioxide, molar mass, which will be 44. And then we'll say, okay, mass is equal to 7.21 times 44, which will be 317.24 grams as the mass in excess that will be left at the end of the chemical reaction. So in other words, if you are provided this amount of carbon dioxide, so a certain amount will react, then you remain with this as excess. So we have come to the end of the video. Now we have the work for practice here. In this one, you have this work which they are saying the reaction between aluminium and iron 3 oxide can generate temperatures approaching 3000 degrees Celsius and is used in welding metals. So we have aluminium plus iron 3 oxide, which forms aluminium 3 oxide plus iron. So this is a reaction and they've balanced it. Then they are saying in one process 124 grams of aluminium here are reacted with 601 gram of iron 3 oxide. All right, then they are saying A, calculate the mass in grams of aluminium 3 oxide formed. Then B, how much of the excess reagent is left at the end of the reaction. All right, so you can answer this question, but I don't know how you are going to know whether you are correct or not. But if you are interested in joining my online tuitions, then you can WhatsApp me on the number that is appearing on the screen right now. See you in my next video. As for now, bye and please, peace.